We are KARURA, an international rover team spanning Japan and the United States. Nearly 100 members from over 25 universities come together across borders and time zones, united by a strong ambition to advance Mars exploration technology. At the University Rover Challenge 2026, we bring our passion, persistence to prove what global student collaboration can achieve.
To tackle harsh Martian terrain, we upgraded our steering, which was in the research phase last year. This four-wheel independent steering enabled diverse maneuvers, including crab arc, arc turn, and point turn. We achieved lightweight yet highly durable structure using generative design with 3D printed metal and high-strength peak components. Furthermore, absolute encoders enable highly accurate navigation. Additionally, compact airless tires and differential mechanism provide driving stability. These advancements ensure reliable mobility performance across diverse terrains and challenging obstacles.
All the rover's electronics are powered from a single integrated power unit, which allows for hot swapping of the battery without shutting down the system. Pressing the emergency stop button cuts off all power via relays. We also monitor battery voltage, power consumption, and remaining capacity in real time with an error of less than 1% to ensure safe operation and to manage energy use when deciding which tasks to perform.
KARURA's comms was upgraded from last year with a dual-band 915 MHz and 5 GHz system, greatly improving our effective range. We utilize omnidirectional antennas on the rover and a custom servo-mounted sector antenna on the base station that dynamically tracks the rover to mitigate prior range limitations. A custom PCB was made for the sub-gigahertz transceiver to improve reliability in a mobile environment. A PySide 6-based GUI provides modular camera feeds and telemetry. Video is streamed from the rover via an RTSP server and decoded using OpenCV, with support for selective stream enabling and video compression to manage bandwidth during long-range operations.
This year, for the first time, we developed a drone to reliably reach the second stage in the delivery mission. It quickly identifies sign numbers and supports fragment search, accelerating team decision and actions.
The ARM team developed an agile system for precision and high-load tasks, and with modular design, each component can be rapidly reinstalled if issues occur. The automatic homing function allows the ARM to return to its initial position even after a system reboot. For the delivery mission, a tray under the body allows many heavy objects to be delivered for longer distances. Preset commands move the ARM to specific poses for fast and consistent operation. Combining inverse kinematics with the controller has led to more intuitive operation and shorter movement paths.
In addition, the compact synchronous gears generate enough torque to climb obstacle while holding 8 kg payload. Automatic typing combines inverse kinetics with computer vision, and the system recognizes key position and perform typing with no direct impact. Through the comprehensive build station, we are running through mission-based tests in a realistic competition flow. Development and operator training continue not only to complete all tasks in equipment and their mission, but also to maximize reliability and efficiency.
Our navigation system is engineered for maximum reliability via a redundant dual GNSS setup, using sensor data fused from 3 independent IMUs. This configuration ensures precise localization and stable odometry, even during sensor failure. To maintain performance in bright desert environments, we integrate VSLAM with LiDAR, which provides a robust foundation for obstacle avoidance. For target acquisition, the rover detects RUC attacks from up to 20 meters away and is programmed to autonomously initiate a spiral search to guarantee reacquisition if visual contact is lost. With all processing and LED status updates running on board, our system can act autonomously even without radio communication. Finally, we utilize YOLO V11 to identify all 3 mission objects in real time from 15 meters.
We have developed 4 scientific analysis methods: microimaging device, Raman spectrometer, multi-spectrum camera, and environmental sensors. Initial field analysis is supported by a front camera, panoramic camera, and the 2 downward-facing surface cameras.
We adapted a clamshell bucket-based handling mechanism. A single-axis arm transports the sample to the rover. After removing rock fragments, it is mixed with water and distributed to model analysis.
Researcher microsystem compact microimaging device are newly able to achieve accuracy detection by combining image contrast analysis with ML negatively stored body components. A Raman spectrometer combines a CMOS camera with custom design optics. The rotating test chip mechanisms help spurs rarely scattering. By analyzing vibration peaks in spectrum patterns, we can infer the likely presence of specific minerals in biomolecules. We custom build a new multispectral camera to estimate surface minerals, and image analysis software outputs color-coded images. Onboard sensor continuously capture environmental conditions. A camera and the gas sensors are mounted at the tip of the sampling arm.
After the site is selected, a core sampler fitted with an outer auger and inner core catcher is driven into the ground by a linear actuator to collect a subsurface sample up to 20 centimeters deep, indicated by the plastic liner. The sample is easily detached by removing the pin.
Through coordinated development between our American and Japanese bases, KARURA is now mission ready for URC 2026. Thanks and Gigam.